This lesson is about stress strain graphs. We've got to look at elastic and plastic deformation of materials. We've got to identify mechanisms for these to happen, just to make us understand why there are different ways that material stretches, and we need to relate some other properties. So far with Young modulus we've only looked at the straight section of stress strain graphs, which is to do with the elastic deformation, but we need to move on a little bit further than that. So here's our first method of deformation. This is elastic deformation. So if you're thinking about why a material might get longer, if these circles represent the copper atoms in a copper wire, if you pull them, one way that it can get longer is for the atoms to pull apart. This is much exaggerated, of course, because this deformation will really be a very, very small amount of strain. But what's happening there is the atoms are getting pulled further apart and they're attracting each other, so if you take that force away, what will happen is it will just go back to its original length. So this is elastic deformation, and because of the nature of the force between these atoms and the separation, it turns out that what happens is if you pull these atoms with twice the force, the separation between them doubles, and this is why we get a proportional relationship. Okay, so for plastic deformation, plastic as in the word plasticine means that when you pull them, they don't go back. Okay, and what happens here is this is a completely different mechanism. So just in simple terms, what happens is an entire layer of atoms slides past the other one. That's made the wire longer, but if you remove the force, these particles, these atoms, won't go back to their original positions. They'll just sit in these new holes. Hopefully you can see from that animation that there's a certain amount of force required to reach this level, because if you pull them a little bit, they're going to just fall straight back into the same holes. But if you pull them far enough, then they won't go back. So these are our basic two methods of deformation: elastic, where it goes back to its original length when you remove the force, and plastic, where the deformation is permanent. Okay, so one of your required practicals for this is to find a stress strain graph, and this is the setup you'll have seen, where we get a wire and we put a load on it, and we measure the stress and we measure the strain, and we get a graph. And so far we've only really talked about this straight line part of the graph, where the stress is proportional to the strain and the Young modulus applies. Okay, we can find the gradient of this part will give us the Young modulus. But beyond that part, okay, here's some results from an experiment we did. What happens is it's no longer proportional, the graph curves, and it's really important that you think about which way around these axes are. This is the strain going this way, so this is a wire which is getting much longer for a relatively small addition to the force applied to it. The stress increases a little bit, the strain increases a lot, and that's because once we go past this point, we've changed the mechanism of deformation. So this is a permanent deformation. If you take the wides off, or when the wire breaks, if you've gone up to here, then you'll lose that initial elastic extension, but you will go back down to a permanently extended wire. Okay, there is a required practical on the finding the Young modulus of copper and plotting the stress strain graph, so it's important you look into that. But this is the kind of graph that we find. Got, again, remember, strain on the x-axis, stress on the y-axis, and we need to know about the key features of this graph. So up the side here we've got straight line. This is our elastic extension, this is where the Young modulus applies, up to this limit of proportionality here, which, just like for the spring, we call the elastic limit. Past the elastic limit, then we start to get a curve, and this is the plastic extension. The part which is hard to find when you do this for real in class is that what actually happens is you reach an ultimate tensile strength. So when the stress goes past this value, the wire is going to break unless you can somehow stop it. So in our experiments, normally what happens is the wire just breaks here and the graph will finish at this point. But in reality, as long as you can stop it breaking, you'll find there's quite a lot more strain, but the stress is going down. So these are the key features of the stress strain graph for a material like copper, but we do need to look at some other materials as well and some other properties. so this one on the end here is the breaking stress. If you go past that, it will break. So here are some other properties. Okay, some materials are said to be brittle, some are stiff, some are ductile. The one that confuses people is brittle, because in everyday language we tend to use the word brittle to mean weak, but in fact brittle doesn't mean weak at all. Brittle means that it does not deform plastically before it breaks. So a material like cast iron, for example, is extremely strong. It's very difficult to break it, but it doesn't deform plastically. The way I like to think about this is, if you can glue it back together again after you've broken it, then it's a brittle material. So you might think like china or something is something that you can glue back together, but if you make something out of cast iron, that will also, you can fit all the pieces back together like a jigsaw afterwards. Stiff is, as you would imagine, a material that is hard to deform, and ductile is a material that you can draw out into a wire. So that needs a large plastic deformation, a deformation which isn't going to disappear as soon as you take the force away. What will those look like on a graph? Okay, well here we've got a straight line graph for A, we've got a straight line graph again for C but with a lower gradient, and then a graph a bit like the one we've just looked at for B, okay, which has got a definite curve to it. So if we try to associate these with our examples, the brittle materials are both A and C, because they have both stretched to breaking without any plastic deformation. The strongest material is A, because this one has taken the greatest stress before it's broken. The ductile material is B. You can't be brittle and ductile, so this is B. This has had a large plastic deformation. The stiffest material is A, because this has the least amount of strain for a given amount of stress. The weakest material is C, because it's broken with the smallest breaking stress, and the least stiff material is also C, because that's stretched a lot for a small amount of stress. Okay, so these are all material properties that we can look at using a stress-strain graph. Okay, a couple of questions here just to finish us off. So here's a fishing line. We've got a 2 metre long fishing line with a cross section of a diameter of 0.5 millimeters. The base Hooke's law up to a 52 millimeter extension at a stress of 1.8 times 10 to the 8 pascals, and the greatest load the line can take is 45 newtons, by which time it's stretched by 88 millimeters. Calculate the value of the Young modulus, so we need to look for which values we need here. Okay, well, the first thing is we need to find the part that obeys Hooke's law where the extension is proportional to the force applied. So that's only this part of the graph up to 52 millimeters. So to find the Young modulus, we do stress divided by strain. The stress we've been told is 1.8 times 10 to the 8 pascals. The strain, remember, is the change in length, the extension 52 millimeters divided by the original length of 2 meters. That gives us 6.9 times 10 to the 9 pascals. The breaking stress, assuming that the wire doesn't get, or the line doesn't get thinner as the force is applied to it, the breaking stress is, well, here's our extension, and we can work out the cross-sectional area. So do that first, like I said before. This is pi r squared, don't get caught out by the diameter. And then we do the stresses, the force area, so 45 divided by the area gives us 2.3 times 10 to the 8 pascals. Okay, to find the breaking strain, we need to do strain as the change in length divided by the original length. 88 times 10 to the minus 3 meters divided by the original length of 2 meters gives us 4.4 times 10 to the minus 2. Okay, hopefully you're thinking, oh, hang on a minute, I've missed the units. But again, it's strain, there are no units. Sketch a graph to show how you'd expect the tensile stress to vary with strain. Okay, so here we go, so stress and strain. We've got some extension, we had 52 millimeters of extension, and then we got another 36 millimeters up to here, and that's the limit of Hooke's law where the line is straight, and this is the breaking point. Okay, our second question, we've got 3 different materials here, copper, glass and hard steel. Which is which in terms of these 3 lines? Well, hopefully you've seen enough now to know that this ductile material is copper. So we need to know that copper is a material you can draw out into wires, for example. That glass, if you break a piece of glass, you can glue the bits back together again. So glass is Z, we can see it's a brittle material, there's no plastic deformation. And steel, hard steel anyway, is a material which has got a fairly steep line, so it's quite hard to deform, but it does have a little bit of plastic deformation at the end before it breaks.